Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we begin Chapter 8 with Chapter 8.2.1, which is Angles of Polygons. So in 8-21, we are going to be copying the pentagon at the right onto our paper. And with our team, we're going to try to determine the sum of the measures of the interior angles of the polygon using any method we want. So it's giving us a little bit of a clue here. It's saying you may want to use the fact that the sum of the interior angles of a triangle is 180 degrees. And so I feel like we're going to have to use that piece of information here. And so what I'm going to do is I'm actually going to just choose any vertex of this pentagon right here. And remember, the vertex, like the vertex of a parabola, is going to be where the two ends meet each other. So I'll go and just choose a random one. I'll stop right here. So this will be my vertex right here. So what I'm going to do is I'm going to go and connect this vertex with an opposite vertex. So I'm not going to connect it with this vertex here. That would be an adjacent one. I'm going to copy it to an opposite vertex, another opposite vertex here, and notice how I can't connect it down here because that doesn't do anything for me. So the reason why they told me to use the fact that the sum of the interior angles of a triangle is 180 degrees is because what I've just done right here is I've created 1, 2, 3 triangles. And so if I wanted to find out the sum of the interior angles, well, what I could do is I could take the fact that there are 3 triangles present in this figure. And if that means that there's 3 triangles, that means that there are 3 180-degree sums in there, which means I've got a total of 540 total degrees as the sum of interior angles of this pentagon. Hopefully that method makes sense because we're going to extend that method into a bunch of different shapes. I'll be back with the next problem. So based on the last problem here, we're going to tackle 8-22 here. And it says in the previous problem, you solved the sum of the measures of the angles inside of a pentagon, but what about other polygons? So we're going to obtain the resource page. We should already have it in front of us, or you can print it off of the CPM website. And we're going to complete this table, and hopefully we can make a generalization for how to find the sum of the interior angles of any type of polygon. And so with 5, we already determined that it was 540. Let's go and determine 4 real quick. So I'm going to go and draw a square, or any kind of 4-sided figure. It doesn't really matter. Oops, I don't know why I put a C right there. I'll go and draw any kind of 4-sided figure. So I don't know, 1, 2, 3, 4. I'll even do it for a square or a rectangle. That way we all know that it's like that. I'll even draw like a parallelogram. And that way we know that it's true for all of these types of polygons here. And so again, I'm going to go and just draw a vertex, just right here. I don't know, right there, here. I don't know, just in random places. And I'm going to go and connect that corner to an opposite corner. Again, I'm not going to attach it to an adjacent corner. That doesn't do anything. But if I connect to this guy, I've now created 2 different triangles. Same thing here. I've connected 2 different triangles. Same thing here. I've connected 2 different triangles. And again, we're using this knowledge that the sum of the interior angles of a triangle is 180 degrees. Well, how many triangles do I have here? In each situation, no matter what type of quadrilateral I have, there's always only 2 triangles, which means I have 180. So which means I've got 180 degrees times 2 of them, which ultimately nets into a 360-degree figure, or a figure that has a total of 360 degrees inside of its interior angles. So let's go ahead and take a 6-sided figure. Now for this, I'm probably going to draw just a regular hexagon because that's the only 6-sided figure I know how to draw. But if you extended this to any, if you extended this to any 6-sided figure, you would see the same thing. And so from here, let's go and just draw the best hexagon we can. Actually, that wasn't too bad. So I'll go and just connect again. So from here, I'll just pick one random point here. I'll just pick this guy. Again, won't connect there, doesn't do anything, but I'll connect there because that got me a triangle. I'll connect there, that got me a triangle. I'll connect there, that gets me a triangle. Again, here, doesn't get me a triangle, so I won't worry about it. So how many triangles do I have? 1, 2, 3, 4. So I've got 4 of those triangles. In other words, 4 times 180. So 4 times 180 is going to get me 720 total degrees. So at this point, I would encourage you to start pausing the video and making sure that you have that you can establish the pattern as well. But if you want to keep on coming along, it's no big deal. So I'm going to try and do my best to draw a 7-sided figure. If I fail, then I will just go and copy one down. Give me a second here. So that's 1, 2, let's see, 3, 4, 5, 6. Oh, I'm going to make it 7. Okay, good job. All right, so now from here, let's go ahead and draw, albeit he looks a little bit weird, but nah, it's all good. Here, I'll go and just map out my triangles again. So 1, 2, 3, 4. So again, 1, 2, 3, 4, 5 triangles inside of a 7-sided figure. Now, if you haven't been following along, I'm hoping that a pattern is starting to emerge here, where when I have 3 sides, that's 1 triangle. 4 sides is 2 triangles. 5 sides got me 3 triangles. 6 sides got me 4 triangles. 7 sides got me 5 triangles. So 5 times 180 is going to get me 900. Whoops, let's switch colors here. 900. So hopefully you've been able to establish a pattern here where we wouldn't really even have to draw an octagon. Not that it's hard, but let's try and guess as to how many triangles will appear in an octagon. So go ahead and take a second and pause and think about it, and think about how many triangles will appear in an octagon, and hopefully you will have guessed that inside of an octagon there will be 6 triangles at 180 degrees per triangle. So 6 times 180 is going to be our good old buddy 1080. And so from here, and that was a guess. We could be wrong, so 1080. But let's see if we draw an octagon, if it ends up becoming that way. So let's see here. 1, 2, 3, 4, 5, 6, 7, 8. And here we go. So 1, 2, 3, 4, and 5. How many triangles is that? 1, 2, 3, 4, 5. Hey, 6. What do you know? We predicted 6 triangles. I think we got 6 triangles. Next, for 100, I'm hoping that by now you will have guessed that there are 98 triangles in the 100-sided figure, and you would be correct. So that means the total angles in a 100-sided figure would be 17,640. Now, in an N triangle, they didn't give us a whole lot of room here, but what they want us to do is they want us to come up with a general formula here. And what this does is it takes the 180, because that's the number of triangles, and we take N, and it looks like every time we're subtracting 2. How do I know? Because 3 minus 2 is 1 triangle. 4 minus 2 is 2 triangles. 5 minus 2, 3 triangles. 6 minus 2, 4 triangles, and blah, 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 blah. So this 180 times N minus 2 is the interior angle sum of a polygon. Interior angle sum of a polygon, where N seems to be the number of sides, in the polygon. So hopefully that makes enough sense. I'll be back with the next problem. I'll be right back. Now that we've found a method to find the sum of all the interior angles of a polygon, let's talk about the interior angles of what we call a regular polygon. What is a regular polygon? Well, a regular polygon, let's define this here, a regular polygon. A regular polygon is a polygon with all sides being equal and all angles being equal. So we've actually talked about regular polygons in the class without even calling them that. The equilateral triangle that you guys learned at the beginning of the year is an example of a regular polygon. So if you look at the hexagon here on the right side, it looks like a regular hexagon, right? All the sides are labeled to be congruent and all the angles are labeled as x, so they'll be the same. And so in the problem 8-23, it reads that Fern is helping a friend with their math homework, and they get stuck trying to determine the value of x. And Fern says, I know how to calculate the sum of all the angles of a hexagon, but how am I supposed to find the individual angle measures? And so Jeremy says, well, this is easy because all the angles are the same, so we can just divide. So what does Jeremy mean? Well, what I'm going to do is I'm going to first find out the sum of the interior angles of a hexagon. How do I do that? Well, a hexagon has 6 sides. So I'm going to say then that 6 sides minus 2, right? Based on the formula we found a few minutes ago, n minus 2 times 180. 6 minus 2 times 180 is going to be 4 times 180, which is 720. So what this 720 is, this is my total angle sum of the hexagon. But I don't want all the angles in the hexagon. I want only one of them. And so what I'm going to do is I'm going to take the 720 and I'm going to divide by the number of angles in the hexagon, which is going to be 6. All right, so what is 720 divided by 6? That's going to be, I believe, 120 degrees. So 120 degrees per angle. Keep that in mind. That's going to be per angle. Now, how can we be so confident that each one's 120 degrees? Because in an equilateral polygon or a regular polygon, all the angles have to be the same measure, so each x has got to be 120 degrees. And Fern is starting to say that that could work for other polygons. Determine the measures of each interior angle of an octagon. Explain how we found our answer. So from here, I'm going to do octagon. So 8 minus 2 times 180. Whoops. And that's going to be 6 times 180. Whoops, again. 180. And that is going to be 1080. And again, what is 1080? That's the total angle sum, right? Total angle sum. But we don't want the total angle sum. We want only one angle. So what's that going to be? That's going to be 1080 divided by 8. And if I know that correctly, I believe it's 135 degrees per angle. 135 degrees per angle. So that should hopefully make a certain degree of sense. Again, we divided by 8 because there are 8 angles in the hexagon, in the octagon. So what about the interior angles of other polygons? What are the measures of the interior angles of a nonagon and a 100gon? So from here, a nonagon has 9 sides. So the non is going to be 9 minus 2 times 180. Keep doing that. Equals, I'll say 7 times 180. So 7 times 180 is going to be 1260. Again, total angles, right? We don't want all the angles. We want one of them. So 1260 divided by 9, right? Because that's the total angles that are there. Each angle in a nonagon, a 9-sided figure, 140 degrees per angle. And let's do with the 100gon. Well, that's going to be 98, or backwards, 100 minus 2 times 180. In other words, 98 times 180. That's what I was going for. So what's 98 times 180? Well, that's going to be 17,640. We talked about that earlier on the table, but now I'm going to take that 17,640 and divide by 100, because that is going to be each individual angle. So 176.4 degrees is the measure of each angle. So the point of this problem here was to first define what a regular polygon is. We will be dealing with regular polygons a lot in this chapter. And so when you hear regular polygon, all the angles are the same, all the sides are the same. We're going to be finding individual angles of regular polygons a lot moving forward. So keep that in mind. I'll be back with the next problem. Let's talk about exterior angles in 8-24 now. So at this question, Jeremy is asking about exterior angles and what can we learn about them. It says, examine the regular hexagon shown at the right. First of all, notice how the problem specifies the hexagon as regular. It says angle A is an example of an exterior angle because it is on the outside of the hexagon and formed by extending one of the hexagon's sides. What can you conclude about the exterior angles of a regular polygon? So, first off, before we even talk about, actually, let's just answer A. So I was looking at B when I was talking about that. What can you conclude about the exterior angles of a regular polygon? Well, what they are is, if you look at them, is they are actually extensions on the outside. So if you look at angle A as a holistic angle, it actually lies on a straight line. So we could probably use some type of 180 minus some type of angles relationship. So I'll go ahead and, oops, whoa, that was not meant to happen. I'll go and write that down for us. Sorry about that. I hate when this program does that. Okay, so we can say that the exterior angle can probably be found, or else be found, by subtracting the interior angle's value from 180, because the exterior angle is here's a word you haven't heard in a long time, is a linear pair to the interior angle. Yeah, there's a blast from the past right there for you. Cool, so that's part A. Now it says, what is the value of part A? So we have to be prepared to share our answer. So from here, let's just go and recount. How do we find the internal angle of a hexagon, of a regular hexagon? So that's going to be 6 minus 2 times 180, which is going to be 720. We've talked about that a couple times now. But 720 divided by 6 is going to be 120 per angle. We talked about that in the last problem. So from here, what I can conclude, and I'll go ahead and just draw kind of a makeshift looking hexagon right here. I know it's not going to be perfect, but who cares? And so assuming this thing is regular, I'll go ahead and actually just use, since it's regular, I'll go ahead and actually just call this angle A. I'll just rotate him out. I know this is 120, so I know that A is going to be 180 minus 120. How do I know? It's because I know that 120 plus A will equal 180 based on a linear pair, right? So I know that A has to equal 60 based on that. So now, what are the sum of the exterior angles of a regular hexagon? Why? Well, from here, since all of the angles are the same, since we're dealing with a regular hexagon right here, let's count how many exterior angles we actually have. So that's going to be, looks like 1, 2, 3, 4, 5, 6 of them. So if I just take 60 and I multiply them by 6, I get 360 degrees. So the total angle sum of all the exterior angles on this hexagon here is going to be 360. Now, I believe I actually made a mistake right here. I apologize. That exterior angle is supposed to be extending this way. No wonder why it looked all weird. Okay, cool. There you go. So now it looks more normal. Okay, cool. So that was C. Let's take a look at D here. What can you determine about the exterior angles of other regular polygons? Explore this with your team. Have each member choose a different regular polygon and analyze from the list below. For each regular polygon, we're going to calculate the measure of one exterior angle and then calculate the sum. All right, so give me a second. I'm going to pause, and then I'll be right back. That way you don't have to watch me draw each of these polygons out. I'll be right back. All right, I've got these shapes in here, so now let's go and calculate the sum of all the exterior angles. We'll find the measure of one exterior angle, and then we'll use that to calculate the sum. So from here on this equilateral triangle here, I'm going to go ahead and extend him out. And whatever I find for this red angle right here, I'll just go and multiply them by 3 since there are 3 of them. And so from here, we know that the measure of the interior angle here is 60. We could totally do the formula, but at this point it's an equilateral triangle. I'm hoping we all know that it's 60, which means each of these angles is worth 120. So 120 here, 120 here. So I know that 120 times 3 of them is 360. Awesome. Seems to coincide with our hexagon. Interesting. So let's go and do the octagon. So again, whatever I find for this angle here, I'm just going to multiply them by 8 because there's 8 of them. So let's go and do just the formula one more time. So I know that it's 8 minus 2 times 180, which is going to be 6 times 180, which is 1080. And if I do 1080 divided by 8, I'm going to get 135. Get 135 per angle. So I know that this is 135, which means if I subtract that from 180, I'm going to get 45 degrees here. Now, if I multiply that by 8, 45 times 8, it's 360 again. Interesting. 360, 360, 360. Let's see if this holds true for the decagon here. So this is the triangle. This is the octagon. This is the decagon. And then this is the dodecagon. 12 sides. So from here, again, 10 minus 2 times 180. So that's going to be 8 times 180. So that's going to end up being 1440. So 1440 divided by 10 is going to be 144 per angle. So that means that this angle right here is worth 144. Extending him out, if I subtract 180 from that, I'm going to get, let's see, 144 minus 180. that's going to end up being 36 degrees. Now, if I multiply them by 10, 36 times 10, well, interesting, that's 360 again. We keep seeing the same number show up here. Dodecagon, that's 12 minus, not 12 minus 10, I'm getting ahead of myself, 12 minus 2 times 180, that's going to be 10 times 180. That's going to be 1,800, right, divided by 12. 1,800 divided by 12 is going to be 150 per angle, 150 degrees per angle. So this guy's 150 right there. So then this angle here is going to be only 30 degrees. But if I take 30 and I multiply them by 12, well, lucky guess here, but I believe it's 360. So let's see if we can't make a generalization about all these exterior angles here in part C here. Or actually, we just did part D. Okay, let's write a conjecture about the sum of the exterior angles of regular polygons based on our observations. So what's our conjecture? Our conjecture should hopefully be something to this effect. A regular polygon's external angles will always sum to 180 degrees. I'll write down conjecture next to that. Okay, cool. I'll be back with the last part of the problem here. Give me a second. I'll be right back. Part F asks about our conjecture from part E. Is it true for all polygons or just only regular polygons? It's actually true for all polygons here. So it's true for all polygons. And the reason why is because in each situation you have an external angle and internal angle interacting. You always end up having a pair of angles, and each of those pairs adds up to 180 degrees. So you've got 180 n, where n is the number of pairs you have. And if you subtract the triangle angle, the polygon angle sum theorem, what you get is, if you do this, you get 180 minus 180n plus 360, and then you end up with 360 no matter what. So this is the sum of your exterior angles on any polygon, not just a regular one. And it says, what is the measure of one exterior angle of a regular n-gon? Well, in this case, this would only work for a regular polygon because we have to make sure that each of the interior angles are the same, which would make all the exterior angles are the same. For a regular, as long as the polygon is regular, as long as the polygon is regular, it's going to be 360 divided by n, where n is the number of angles, which is always the same as the number of sides. So, bit of a long lesson, but hopefully you found this useful. As always, please leave questions or comments in the comments area. Welcome to Chapter 8, and we will continue our polygon journey into the next episode. See ya.